Okay, let's move on to general relativity. Okay, here we have the starting point, very straightforward. Okay, general relativity says that gravity is the warpage of time, bending of time. That's what they say is gravity. Okay, so here it is illustrated for you. Okay, we have the seconds, and the reason the Earth doesn't fly out of the solar system is because there's a wall of seconds, a wall of minutes, a wall of years, maybe decades, centuries, that prevents the Earth from flying out of there. Okay, I did it with seconds because I don't really know which unit they're using. Okay, so all I can tell you is that this is what general relativity says. It says that time is warped. Okay, there's this four-dimensional entity. One of the legs of that entity is known as time. It's measured in seconds. It's you could say, a parameter that is very important to mathematical physics. And what they do, they bend this time. They call it a dimension, right? And this bent dimension apparently serves as a wall to the Earth, so the Earth doesn't fly out of the solar system because the seconds are warped. Okay, actually, that's not totally true because it comes from Einstein's equation. Okay, and Einstein's equation is a field equation. Let me remove this here. It's a field equation. Okay. What is a field? Well, as we saw a minute ago, a field is just a bunch of numbers. It's a set of numbers. And what, in the case of gravity, but really all fields for that matter, all they're talking about is that numbers decrease, or you could say the force becomes weaker the farther you get away from ground zero. That's the notion of a field. It's a bunch of numbers, a set of numbers, spherical shell, encapsulating ground zero, right? So it's a spherical shell of different strengths of whatever, of electricity, of magnetism, gravity. So the farther away you get from ground zero, from the center point, whatever it is, could be the Earth for gravity, it could be the Earth for magnetism, and so on. It could be a charge, a little stick of electricity, and from there, electricity, magnetism, gravity all decreases in strength as you get farther away. So a field is just a bunch of numbers that they can measure. They say, well, the field strength here is so much, and over here, farther out, it's weaker, and closer to the thing, it's stronger. That's what a field is. Okay, so here it is. Let's put that same thing. First, let's find out what the definition of field is again here. We have field, a quantity, okay, represented by a number that has a value for each point in space and time. So what is a field? It's a quantity. It's a number, okay? It's represented by a number that has value. We're talking all numbers, right? Amounts, quantities, right? For each point, location, okay, in space and time. So that's what a field is. And so the question here is, that's, you see it there illustrated. That's what a field is, a bunch of numbers. They get weaker and weaker. I illustrated here becoming smaller and smaller, okay? That's what a field is, a bunch of numbers surrounding an object. That's what it is. Whether you talk about a gravitational field, electric field, or magnetic field, that's what a field is. Okay, so let's illustrate this with the Earth. Let's find out what prevents the Earth from flying out. I said a minute ago that it was time. You've got warpage of time. Could be the seconds are warped. They turn these things into physical objects. These words, right? They turn them into physical objects. And here you have it. Here's the field, also around the Earth. Okay, so the Earth goes around, and what you have is these numbers, and they're vibrating because the field is vibrating numbers. They wiggle back and forth, they up and down in different directions. Okay, so it's not like the Earth just goes around and circles around nothing, right? Or on top of nothing. There is something there, and they call it a field. And so the first question you should ask yourself is, hold it, what does field have to do with time? Because if on the one hand you have time serving as a wall, as a dimension that is curved around and prevents the Earth from flying out, because they're saying it's warp space-time, right? That prevents the Earth from flying outwards. Then how does a field, which is a bunch of numbers that just decrease in strength from ground zero, how does one thing have anything to do with the other? How do you reconcile field with time? That's the question. Okay, because field is just a bunch of numbers that are weaker as you get out, right? From, say, the sun in this case. The sun is the center of our system here. We're talking about the sun and the Earth, right? The center of the sun is where the biggest point for the field is, the strongest point. And as you get out, it gets weaker and weaker and weaker all the way to the Earth. Okay, so the gravitational field gets weaker as it gets farther away from the sun until you get to the Earth, and even weaker as you get farther out. Great. what does that have to do with the wall of time, warp space time, right? That serves as the depression along which the Earth rolls around like a little ball on a roulette. That's the question. So what does field have to do with time? Which one is the true mechanism? They say Einstein's is a field theory. And then on the other hand, they say warp time is what prevents the Earth from flying out. So, you try to make sense of that. I don't think you can make sense of either one of them, but they seem like they're contradicting each other. Okay, in order to get to how do we come up with all this nonsense? General relativity, poppycock. Well, we got to start all the way to Newton, 17th century, okay? So let's bring Mr. Newton in, and he came up with an equation. Really, he wasn't the originator of the equation. It was the French who later on developed the equation. He's given the credit because he's the guy who said mass divided by distance squared. In other words, you have two masses, two objects, and we're looking at the weight, the mass of each one, right? And it's inversely proportional to the square of the distance. That's essentially what Newton said. He didn't even have the gravitational constant g at the time. Okay, he just said, look, there's this inverse relation to distance. Okay, between the masses. Okay, and so this is what it looks like. Okay, here's Newton's equation. It says force equals gravitational constant g, mass. Multiply those divided by distance squared, and that gives you the gravitational force. Okay, two masses separated by distance. The big problem is, he said, hypothesis non fingo. He wrote in Latin. Okay, they did in those days. That was the English of those days. Everybody who was educated would talk or write in Latin. Turns out, he says, hypothesis non fingo, meaning he doesn't have any theory. He doesn't have an explanation for how that works. Okay, what he had is a description, mathematical description, but not a theory. He did not have an explanation, a physical interpretation of how gravity works. And to this day, no one in mathematical physics has one. And he was a particle man. He believed in the ether also. And so, he could not imagine how particles going out from the Earth and going out from the sun could attract one another. So he said, he couldn't explain this. He said, I have no explanation for how this works. And here's his words. And they come from the Principia and from a letter he sent to Bentley. Okay, and the first one he says in the letter to Bentley, he says that gravity should be essential to matter so that one body may act upon another at a distance through a vacuum without the mediation of anything else. Okay, without a mediator, right? By and through which their action and force may be conveyed from one to another is to me so great an absurdity that I believe no man who has competent faculty of thinking can ever fall into it. He continues, says, gravity must be caused by an agent acting constantly according to certain laws. Okay, so there's got to be a mediator, an agent. Okay, he said there's got to be something in there. Okay, what was the problem? He couldn't see or touch anything between two atoms or between two objects. So he says gravity must be caused by an agent acting constantly according to certain laws, but whether this agent is material or immaterial, I have left open to the consideration of my readers. So he says, I have no theory. I'll let you figure it out. You come up with whatever you want, but I'm just going to describe, essentially. In other words, he was not a theorist. All he was is a mathematician. What do mathematicians do? Well, they describe. They can only describe. That's all that mathematics can do. It cannot explain anything. And that's why Newton could not explain a single thing. And then he continued in Principia, he says, and this is the version of 1713, he also wrote in 1687, I have not as yet been able to discover the reason for these properties of gravity from phenomena, and I do not feign hypothesis. Again, no, fingo non hypothesis, right? And he says hypothesis, whether metaphysical or physical, listen to this, whether of occult qualities or mechanical, have no place in experimental philosophy, meaning mathemagics, okay? So here you can see what happened in the 17th century so-called scientific revolution. They said, look, we don't care about the explanation. We don't care about the physical interpretation. We don't care about any of that. What we care about is experiments, right? In experimental philosophy, he said, we care about experiments. We care about describing them mathematically, and that's it, measurement. But he had no explanation. He said, well, we don't care about that. Okay? He said, it is enough that gravity does really exist and act according to the laws which we have explained. No, you haven't explained anything, Newt. You've only described. Explanation means that you can explain, give us a physical interpretation, right, of the causes and mechanism. And obviously he was not able to do that. And so he says that all he can do is describe essentially the motions of the celestial objects and the sea, etc. So all that Newt could do was describe. Okay, that was his folly. He says, look, all I can do is describe. And he called it an explanation, which it wasn't. to this day, we have no explanation forthcoming from the establishment, mathematical establishment, and I recommend that you do not hold your breath. Okay. Okay. Just in case, he used particles, and particles can only push. But even if you replace them with like Robert Hooke's waves, right? He's the guy who came up first with the longitudinal waves. Later, they were converted into transverse waves by in the early 19th century folks. Okay, and Fresnel and Fizeau and some of the other Frenchmen there. And here you see what happens with a wave. Wave only pushes. Okay, there is no wave that attracts. You cannot attract with a wave. Wave can only push. So whether you use particles or waves, you're going to be pushing. Okay, and so the question is, how do you produce pull with push? Okay, and that's when Mr. Einstein comes in. He changed a little bit, quite a bit, the physical interpretation of gravity. And he got rid of Newton. He said, look, yeah, this thing that you got, force, particles, waves, none of those work really. We do it differently in general relativity. How do they do it? He said he did it with this field, this supposedly medium that pervades everything in the universe. In other words, space is itself a physical medium in general relativity. They call it space-time. Before then, they call it the ether. It's the same nonsense, just different words. Essentially, he says there's this medium. This medium is made of particles, just like the ether is, no different. And what are those particles? They're really locations of where you're going to measure something. Okay, and that's where quantum intersects, you could say, with general relativity, with space-time. Okay, so here's Einstein. He changed that. He's going to do it with push. But it's listen to how he does his push gravity. He does it a little differently than Newton. Newton threw particles back and forth. He says, I can't explain it with that. How does Einstein explain it? And here it gives you an idea. He's got this equation. Left-hand side is space-time curvature. Right-hand side is the source. In other words, the source, in this case, bends space-time downwards. It's bending time downwards. And because of that, space-time is warped, and that forces the moon to roll around the Earth. Okay, so that's essentially the physical interpretation. We do not care at all about Einstein's equation. He can do all the equations he wants. When he comes into physics, he's got to explain how gravity works. And this is his explanation. This is the explanation of relativity. And we take it literally. We don't take it as an analogy at all. It either is or it ain't. You can't say this is just an analogy. No, if it's an analogy of what? If you're going to later on say, well, I deny all of this. There is no depression. There is no moon going around this depression. And the Earth doesn't push a canvas downwards. Then what was the purpose of the analogy if you're later on going to deny it? Either this is or it ain't. And you have a statement from Mr. Wheeler, John Wheeler, who synthesizes, says, space-time tells matter how to move, matter tells space-time how to curve. That's essentially what the equation says. That's what it tells us. Okay. Okay, what happened was that, well, you have all the mathematicians. This was in 1915 when Einstein came up with his field equation. And all the mathematicians, well, not all of them, in fact, very few at the first, did like his idea, said it's different. Why? They liked it because suddenly they had a different physical interpretation for how gravity works. And that's great. If you've got a better interpretation, let's look at it, And one of the things that eventually came out is that Einstein's equation was a little more accurate than Newton's, especially when they had to describe the orbit of Mercury. Okay, whereas Newton has two masses separated by distance, in this case, Mercury and the Sun. Einstein's equation, what they did, the field equations, what they did was they looked at a point mass that's going around the Sun. So we have a point mass going around another mass. That's all they looked at. They don't look at objects. They don't look at things. They said that we have a point mass going around, and what Einstein's equation does is it describes the itinerary of that little point mass. And so it turns out that Mercury's perihelion shift, let's say this right, Mercury's perihelion would shift over time. It would, shift and form like a rosetta over many orbits. And because of that, they weren't able to explain that with Newton's equation. They were able to explain it a little, or describe it really, with Einstein's equation. And so they said, well, Einstein's equation is a little more accurate than Newton. It's a little closer. It wasn't perfect either, but it got closer. A lot of people say that he fudged the numbers to get them closer. Fine, that's, opinions there. But the point is that the mathematicians later on, when they finally bought into his theory, his description, his equation, field equation. Oh, the reason is, well, the main reason was that, or one of the main reasons was that it was more accurate than Newton's. Okay, and so here's an analogy. Okay, here we have two mathematicians. Mathematician A, he comes up with an equation and he says, look, I measured, I did this, I did my calculations, and he ends up with a straight line. That's his equation describes a straight line. Another mathematician, he's a little more sophisticated maybe, and he goes in there, he measures, he does his calculation. He says, well, it's not quite a straight line. I think it's like a curvature. So now he gets the Nobel Prize. Why? Because he's got a more accurate equation that reflects what they've been studying. But see, all they're doing is ad hoc stuff. They're tailoring the equations to their measurements. And once they discover that the measurement is not exactly what they thought it was, and they perfect the measurement, they say, oh, we made an advance. And all they're doing is tailoring the math to what they observe. So mathematics is a tautology as it's applied to mathematical physics. It's a tautology. All they do is measure and come up with an equation. And once they have that equation, boy, it had better meet, they say we can predict. Yeah, of course you can predict. You can predict because you did it 100 times. You finally tweak the equation to the point where it matches exactly. And now you can say, oh, we can predict. And so what? You still haven't explained anything. You haven't explained the cause of gravity. You haven't explained the cause of magnetism, but you can predict that a magnet attracts another, or that, this spoon will fall to the table. Great, you can predict. And you can tell me exactly how fast and what the acceleration is and get all the numbers right, but you still cannot tell me what the cause of gravity is. Okay, and so that's where we stand today. And that's what they dismiss as philosophy. Okay, here we have one of the things that Einstein apparently explained, and it's the Mercury-perihelion shift. You can see that the orbit is shifting over time. That's more or less what's happening with Mercury's perihelion. And they thought originally they thought Leverrier was one of the fellows, a French guy who discovered Neptune. He thought, the same thing. We have a planet there somewhere between the Mercury and the Sun, and they called it Vulcan. And they were looking for this planet over decades. They finally gave up. They said, there is no planet there. We can't find it no matter what we do. And Einstein came up with his equation and said, I can explain it. In other words, describe it. I can describe the orbit of Mercury better than Newton. And with that, they said, okay, now we like it, because not only could Einstein describe it, the orbit, better, but he also, on top of that, he was able to do a second thing, which was this here, which happened 4 years after his equation. He came up with his equation at the end of 1915, and then by 1919, Mr. Eddington, head honcho over there in England, right, merry old England, and he came up with this. He was able to prove Einstein's prediction that light curves around the sun during an eclipse. And so, Eddington gave some kudos to Einstein, and the New York Times picked it up. And from that time, Einstein became a household word. Okay? Everybody knew Einstein after that, because he had predicted the curvature of the sun, of the light around the sun. Okay. Okay, but how does Einstein do his gravity? Well, he does it also through push. Okay, but it's a funny way he does push. And here it is. Okay, I want you to see this. This is how gravity in general relativity is done through push. Okay, so how do you pull with push? Here you'll see it. Okay, first you build this thing, a bowl, and you push it down with that green ball, whatever that green ball, so it weighs it downwards. So the ball is weighing down. It means it's pushing, okay, the flexible, the malleable green bowl downwards. Okay, and this compels or induces something to go around the edge of the bowl. Okay. And so what does that little thing do, the little red ball? Well, it's pushing outwards. So in both cases, you have push. You have push downwards and push sideways. And the only reason Einstein could get away with it is that you have a continuous bowl. Okay, so that was his insight, the fact that he's got a continuous object, which is the bowl in this case, but he's doing it through push. He pushes downwards and outwards, and that's how he's going to explain gravity. Okay, so it's important to know that unlike Newton, who said, look, we have particles going back and forth, force. Einstein said, no, we have mass weighing down, right? Meaning it's going to push the canvas downwards, and the other one's going to push towards the side of the bowl, just like a roulette, But then the issue is, why does the green ball, push downwards? So good old Einstein is invoking gravity force, right? Newton's force, Newton's gravity, to explain gravity. Okay, that's what he's doing. He's saying gravity is like this. Look, we have a force to start out with that pushes the canvas downwards. Okay, that's push, and then the other one has no other choice but to roll around. Why does it fall inside the hole? Well, we don't know. It just keeps rolling around forever. And of course, you cannot explain this with a three-body system. You can only explain it with two. Okay, that's another issue. Okay, and because of that, you have these people who say that you have all these ripples, these waves that go along space-time, and they say those cannot travel faster than the speed of light because the speed of light is the speed limit of the universe, and so no wave can travel faster. And but a wave travels one way also. So they discovered a couple years ago, they discovered gravitational waves from two black holes that allegedly collided. They got a Nobel for all that stuff. And the question is, that wave comes one way. So let's assume two black holes collide. Lots of mass, great, let's concede all that. So two black holes, heavy as the entire universe, they collide and they create waves. Great, these waves come towards us. How does that produce attraction towards the two black holes? That's what we have no idea of. And so here you have, because the mathematicians say, look, if the sun were to disappear, all these gravitational waves, they can't travel faster than light, so we would not fly out immediately from the solar system, us being the Earth, right? We would not fly out instantly. It would take 8 minutes for all those waves to travel to the Earth along space-time. So here you're rolling around time, right? Because time is curved and does not allow the Earth to fly outwards, right? Time is curved there. And here you have these waves that come along space-time, I guess. Time is all the way to the Earth, to the sun. They come along there no faster than the speed of light, and until that sun disappears and there's no mass weighing down the canvas, we don't fly out. And this is an illustration of that. Here you see it, okay? So according to relativity, if the sun were to disappear, it would take 8 minutes for the Earth to fly out of the solar system because gravity cannot travel faster than light. Okay, so this is the notion that we have today, and there you have space-time, all those, that canvas there, that space-time, you can see the waves coming towards the Earth. Okay, but what's the issue? The issue is that they treat space and time as physical objects, meaning time is a physical object because it's one of the legs of space-time, four-dimensional space-time. Okay, and so, well, there you have it. That's the party line. That's what you will learn if you go to the university, and now you're an expert in general relativity. There's no more than that for the theory, for the explanation, for the physical interpretation. We don't care about the math. They can do all the math they want. When they come to the conference, we want to explain the physical mechanism. Okay, and so we don't need to curve space-time, okay, like Mr. Eddington did, with the light moving around the sun. And here's a comparison between what he did and how we do it under the rope model, okay. According to him, light curves around the sun, so we have star far away, and that light from that star curves around the corona of the sun. Okay, that's the way Einstein saw it. Why does it curve? Because it follows the curved path of space-time, meaning time is a physical object, time is curved, and light travels along or slides along, or rolls along, I don't know, along this curved path of time. How do we do it? Well, we do it a little differently. We do it all with straight lines. We say that light is mediated by a rope, which is under tension between any two atoms. So it's always taut. That rope is always taut. Okay. And what happens is that light propagates along this rope from one atom to the next. And from the star very far away to an atom that forms the corona of the sun, it is relayed from that star, from that atom that's doing its quantum jump, it's relayed from there to the Earth. In other words, you do it all with straight lines. You have one straight line from an atom in the star to an atom that forms the corona of the sun, and that atom is titillating. It's expanding and contracting, doing its quantum jump, and from there it relays that same impulse all the way to your eye, and that's why we see it. So we do it all with straight lines, no curvature. Light never curves. Only after 10 beers it might curve, but otherwise I don't think so. Okay, so what do we have? Let's compare here. We're going to compare what general relativity proposes. It's got this canvas, which is space-time, supposedly four-dimensional. They put it in a three-dimensional version because they cannot illustrate what they're talking about, and you have to accept it as is. And here's the rope model of the same thing, okay? Here you see it. We say that all atoms of the sun are interconnected with all atoms of the earth, and the sun essentially swings the earth around itself by these ropes that physically connect every single atom of both objects. Okay, so that's it. You can get an idea from there how easy it is. The reason the earth doesn't slow down significantly, at least, is because space is nothing. So the earth has no way of rubbing its elbow against the space because there's nothing there. Space is nothing. It's not a thing like in relativity. Okay, in relativity, space is a physical object. It's the ether. They call it space-time. They gave it 4 dimensions. They say it's unimaginable. They go through all this rigmarole. Under rope, it's very simple. It's just the ropes connecting every atom, and there is no such thing as space. Space is nothing, and so the earth has no friction with space, and that's why it rolls around forever, pretty much, unless there are other objects, okay, that are affecting the earth, like other planets and other things that are out there in space. Okay, you say, where did you get this notion, Bill, that we're interconnected, that the earth is connected to the sun, that the that the moon is connected to the earth? Well, I showed this the other day. I'm going to show it one more time. If you listen carefully, maybe you learn something. Okay, here it goes. Okay, this is Mr. Brian Greene, and he's going to tell us how the moon is connected to the earth.
How does gravity actually work? How does the earth pull on the moon across hundreds of thousands of miles of empty space? They behave as if they're connected by some kind of invisible rope.
They behave as if they're connected by some kind of invisible rope. They behave as if they're connected by some kind of invisible rope.
But everyone knew that wasn't true.
Okay, so what did Mr. Greene say? He says that it's as if we're connected to the moon by an invisible rope, but that obviously cannot be so. Why? Because they had the wrong definition, or an irrational definition, which they still have, of the word object. They think an object is that which you can see or touch, so they go to the lab and they say, let's run an experiment to see and touch the mediator of gravity, the mediator of magnetism. Now, you can't do that. You can't see or touch the mediators that Mother Nature uses. They're invisible, intangible. Yes, there are invisible, intangible objects. Noumena, that we talked about a couple weeks ago. Yeah, these noumena, they're invisible, intangible objects. And they're one of the so-called philosophers said, noumena are objects of the mind. In other words, you have to visualize them. You have to imagine them. You can't go there and see and touch them. Okay? But if you make the assumption that those invisible, intangible objects, mediators, are there, then you can explain the universe very easily. It's only when you do black magic and you say everything is action at a distance. Entanglement, the gluon that connects 2 quarks, they do it all through action at a distance. And gravity, you have all these action at a distance. And yeah, if you're going to do action at a distance, you're doing black magic. Okay, so here you have another testimony of how everything is interconnected. I showed this last time as well, so here it goes one more time. Pay attention. Here you have Mr. Richard Muller from Berkeley, and he tells you how it is.
What's the force of gravity on me? It's the pull of the Earth on my body. So, for example, if you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay, so we're all connected. Every atom in the universe is connected to all other atoms. You're connected to every atom on Earth physically. Otherwise, you wouldn't be pulling on every atom on Earth, and every atom on Earth wouldn't be pulling on every atom of your body. And until you get that through your thick skull, you're going to be doing black magic, because you're saying that all these things happen through action at a distance with no mediator. Why? Because you can't see or touch it. That's the whole issue. That is the whole issue. Once you concede that Mother Nature works with invisible, intangible mediators, then you can understand how the universe works. And you forget about all the nonsense that all these mathematicians have been doing since the days of the Greek. Okay, here's a situation. You see this, okay? You go out there in the middle of the field and you see this, okay? You see a fellow pulling on a donkey. but you can't see the mediator. You're too far away. You say, how is he pulling on the donkey? Is it black magic? He just goes like this and the donkey comes towards him? Okay, so what are you going to use? Are you going to use stones, rocks, pebbles? Are you going to throw, is that how you're going to pull on the donkey? You're going to do it the Newtonian way? You're going to do it by throwing stones at it? Force? You're going to push stones to the face of the donkey, and that's how you pull them? And or are you going to do it maybe with waves? Here's a different way of doing it. This is the wave. Again, the waves go outwards. How is it that you pull with waves? Which is one of the ways that general relativity offers. They say that waves travel along space-time. So, okay, so you have waves traveling in space-time. Let's concede all that. Let's grant those hypotheses. So how does the fact that the wave goes outward pull the donkey inwards? Okay. Now here's a fourth way that you can ponder, and that's using a rope. And you just pull on the donkey. Now wasn't that so simple? Okay. So you have to decide, what mechanism you're going to use to produce gravity. And again, the issue there is, what is the physical mediator? Are you going to use stones, particles? Are you going to use waves? Are you going to use a rope? Maybe the bowl that Einstein used, the canvas. And there's another way, and that's the Casimir way. And the Casimir way is that you remove particles between the puller and the donkey. Okay, and this is what you get. Okay, you have, this is the Casimir way. And what you have is, what you go in there and remove the particles that separate you from the donkey. Okay, and once you remove that, what happens is you have all these particles from behind the donkey and behind you, and those pull you together. That's the Casimir way. And they call it Casimir. He came up with that in 1948. Okay, he wrote a paper then. But the idea already came from Rediker and Kramer and Lesage. He's also given great merits for coming up with that. But Lesage got it from Fascio and Fascio from Lucretius. So all these people already had that idea of what is known as shadow gravity or shadow pull, where you remove whatever's between them and whatever's outside them pushes them together. That's the notion that Casimir came up with in his great mind, Yeah, and that's what they use today. Instead of saying, look, there's a physical object that's pulling, they're saying, no, we do it a different way. We remove whatever in between and, the two objects come together. Okay, so that's in a nutshell general relativity. What is it essentially? It's a platform means the space-time, time, whichever one you want. There's this ether out there that they call space-time. In the case of general relativity, it's a mathematical contraption, which is four-dimensional, which is not really four-dimensional. What it is four-number-lined, okay? Because mathematics doesn't have dimensions at all, or coordinates, or vectors. What they have is number lines. Everything has magnitude, and what they don't have is direction, okay, or perpendicularity, orthogonality, okay? And a dimension is exactly the opposite. It has orthogonality and direction. What it doesn't have, length, width, and height, what they don't have is magnitude at all. Okay, so that's essentially, what four-dimensional space-time is. The gravitational mechanism is that, you have simply something weighing down the canvas and the other object rolls around. You can't do it with three objects. You can only simulate it with two objects, and then they tell you, well, the analogy is worthless anyway, so we don't care about that. All they care about is the mathematics. And so if you care about understanding gravity and you want to ask the question, how does gravity work? You'll never find out from general relativity, because that's what they're going to tell you, and then they're going to deny it at the end of the story and say, well, you're not supposed to take the analogy. So literally, that's the answer you get.